The dotted address 192.168.10.2 is represented in binary form as shown on the slide. To convert this to hexadecimal, create groups of 4 digits. Each of the groups is assigned a base 16 number, 1 through 9. A represents 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. The first group of digits in the address is 12. This is hexadecimal C. The second group is 0. The third group is 10, which is a hexadecimal A. The fourth group is 8, which is the same in hexadecimal, and so on. Therefore, the address is represented in hexadecimal as C0A80A02. The prefix 0x means hexadecimal. In the next slide, let us understand how to convert hexadecimal to decimal. To convert hexadecimal C0A8 into decimal, first convert each hexadecimal digit to binary as shown on the slide. Gather 8 bits into each group. Now this should look familiar. It is straightforward binary to decimal conversion. We have converted the first 2 octets of an IPv4 address, 192.168. Let us move on to Internet Protocol version 6 in the following slide. The Internet Corporation for Assigned Names and Numbers, ICANN, coordinates the Internet Assigned Numbers Authority IANA functions. This means that they assign blocks of IPv4 and IPv6 addresses to regional Internet registries. Internet service providers normally acquire addresses from these registries. Most companies are assigned addresses by their ISP. IPv4 is running out of addresses, thus a move to IPv6 is imminent. The advantages of IPv6 are: IPv6 provides 2 to the 128th power, or 3.4 times 10 to the 38th power, addresses versus 2 to the 32nd power, or 4.3 billion addresses provided by IPv4. The increase in the number of addresses is the biggest benefit of IPv6. The blocks of IPv6 addresses are allocated to make aggregation easier than IPv4. The need for a network address translation, port address translation, NAT/PAT, does not exist. In fact, in IPv6, there are multiple addresses per interface. IPsec security and mobility support is inherent in IPv6. ICMP v6 messages are sent in IPv6 packets. In IPv4, ICMP v4 is a separate protocol. IPv6 performs maximum transmission unit MTU discovery in combination with ICMP v6. IPv6 determines the appropriate MTU size. Let us discuss IPv6 packet structure in the next slide. The IPv6 header is 320 bits, twice as large as an IPv4 header. The flow label field keeps track of packets that are part of Transmission Control Protocol (TCP) or User Datagram Protocol (UDP) connection. The next header field refers to extension headers that handle options more efficiently than the options field in an IPv4 packet. The header is 64-bit aligned. This accommodates hardware-based processing. In the next slide, let us discuss types of IPv6 addresses. There are 3 general types of IPv6 addresses: unicast, multicast, and anycast. A unicast address is sent to one node on the network. There are 3 kinds of unicast addresses. The first is a global unicast address in the address range 2000:3. These are routable over the Internet. A unique local address is in the range FD00:8 and can be used within one site. A link local address, which uses the range FE80:10, is used only within a subnet. The second general type of IPv6 address is multicast. As in IPv4, a multicast address is sent to a group of nodes on the network. The third type of IPv6 address is anycast. There is no analog to this in the IPv4 world. An Anycast address can be assigned to multiple interfaces. The packet finds its way to the nearest interface with that address. In the next slide, let us learn how to represent IPv6 addresses. IPv6 addresses have 128 bits. They are written as 8 groups of 4 hexadecimal digits separated by a colon. These groups are called quartets. On the slide, view the 8 quartets in the address. There are 3 parts to an IPv6 address. The first 3 quartets represent the equivalent of an IPv4 network. This is the IPv6 address prefix of 48 bits. A prefix would be assigned by the ISP to a company. The next quartet, 16 bits, is the equivalent of an IPv4 subnet. The host or interface identifier is the remaining 64 bits, or 4 quartets. The terminology of prefix and subnets is used differently in various sources. Sometimes the term prefix refers to the first 64 bits. In the next slide, let us discuss how to configure IPv6. To enable IPv6 routing, enter the IPv6 unicast routing command. The most common mistake in IPv6 configurations is forgetting to enter this command. To be more precise, configuring IPv6 interface addresses is possible without first entering the command. However, IPv6 routing will not be successful. There are plenty of public IPv6 addresses available. Each device on the LAN can be assigned 1. In fact, they are normally assigned more than 1. Link local addresses are usually not configured manually. The IPv6 enable command on the interface creates a link local using a modified MAC address called an Extended Unique Identifier, UE64. There are 4 options for configuring IPv6 addresses. The first is static configuration, where the entire IPv6 address is manually entered. The second option is static configuration with UE64 address configuration. The first 64 bits are configured, then the UE64 is added. The third option to configure IPv6 addresses is dynamic configuration using DHCP. This uses stateful DHCP v6. The last option is dynamic configuration, with UE64 using stateless address auto-configuration, SLAC. As you can see, UE64 is often in IPv6. Let us discuss the last 2 options in the following slides.